Hello, welcome back to Larry's Classroom. We're going to start by talking a little bit about current. If we have a piece of copper wire, we have a multitude of available electrons which are negatively charged to carry current through this wire. Now, there will be no current flow if you do not have a potential difference. So in our case here, we're going to hook up a battery. And this battery has a potential difference. So we have a negative Q charge here, and a positive Q charge here. Now this difference in charge will cause the electrons to tend to move in this direction because they will be repelled by the negative charge on this end of the wire, and they'll be attracted by the positive charge on this end of the wire. And we call this electric current, or in this case it's electron current because our charge carriers are electrons. The electrons in the wire, as the current flows, we will have an electron come in on this end supplied by the battery, and on the other end will come out another electron to return to the battery. Now the speed at which that electron flows, the electron itself does not move as fast as the current moves. You've probably heard that an electric current travels at the speed of the light. Well, what that means is an electron comes out here, and roughly the time it takes for the speed of light to get to the other end of the wire, an electron will come out of the other end. But it will not be the same electron. These electrons in here are moving at a slower rate, and so it's the time it takes from one to come in to another one to come out that really is happening near the speed of light. The individual electrons, because there's so many of them drifting, do not have to move as fast as that speed of light speed to get to the other end, to have a current show up at the other end in that amount of time. Now, electrons only move with a potential difference, which we've supplied here by the battery. If we are to remove the potential difference, we will have a drift of electrons, but they'll be random. Some of them will move in this direction, some of them will move in this direction, some of them move this way and that way. But the net number of electrons passing a given point will always equal zero. As many as go to the right as will go to the left. So there will be no actual current flow without a potential difference. And we'll put the battery back in here, supplying our potential difference, which leads to our electron flow traveling. In this case, we're basically making a clockwise direction around this here loop. And in a copper wire, as in most metals, they're good conductors, so the electrons are easily passed from atom to atom to atom. And that's why the resistance of a wire, a copper wire, is fairly low, much, much lower than other things such as carbon. Now, some examples. We removed the battery, and we found that there was no current flow. Another way we can have, if we just connect the ends of the wire together, we also have no potential difference because both ends of the wire are connected. They're at the same potential. If the wire just out there in space with nothing connected to it. Again, no potential difference provided by the air, so we don't really get any current flow. We need the charge carriers, which in this case are the electrons, which are relatively plentiful and easily pass from atom to atom in the copper wire. We need the potential difference provided by the battery in this case, which gives us a electric current flow in this direction. Now, current, let's talk about what we call the ampere. 1 ampere equals of electron current equals 6.25 times 10 to the 18th electrons flowing past a point. So if we had, we'll just put a little arrow here and we'll call this point 1. If we have 1 ampere of current, which we often call amps, flowing in this wire, there will be 6.25 times 10 to the 18th electrons will move from this side to that side of that line that we have put in here next to point 1 in 1 second. There might be some move this way and some move that way, but most of them will be moving in the direction that the charges cause them to move due to the potential difference. And the net difference, basically, if we had 1 electron move this way, there would be 6.25 times 10 to the 18th plus 1 moving that way. So our net flow of electrons in this electron current flow at 1 amp will be 6.25 times 10 to the 18th electrons moving from the left to the right during each second. If we had, instead of 6.25, we have 12.5 times 10 to the 18th electrons moving past this point in 1 second. That would be a current of 2. I'm going to go per second here. 2 amps or 2 amperes. And current in this loop will be the same anywhere. If we put a point 2 here, we'll find the same number of electrons flowing past point 2 as are flowing past point 1, and in the same direction. If we have a point 3 just where it comes out of the battery, it's the same thing. If we have 12.5 times 10 to the 18th 2 amp current flow, we will have 12.5 times 10 to the 18th electrons each second past this point, 12.5 times 10 to the 18th electrons past this point, 12.5 times 10 to the 18th electrons past this point, all going in the same direction. So we've talked about 2 things: how much charge in a given amount of time equals an ampere. We've also discussed the fact that the current in this loop is the same everywhere. Now let's talk a little bit about the difference between current and charge. Current we saw to be amount of charge in a given amount of time. We use the symbol I to represent current, which stands for intensity. I'm going to write that in. And we measure that in amperes. And we can say that I is equal to Q, which is our charge, in coulombs, divided by our time in seconds. And that's what we demonstrated just a few minutes ago. That the charge, if we have 1 coulomb per second traveling past this point, we would have 1 amp. If we had 2 coulombs per second traveling past any point in this loop, we would have 2 amps. If we had 2 coulombs in 2 seconds, that would be 1 amp, because we've doubled the amount of the charge, but we've also doubled the time. So we could say that 2 coulombs in 2 seconds equals 1 amp. But you notice this fraction can be reduced. That's the same as 1 coulomb in 1 second equals 1 amp. So the amount of charge that traveled past a given point in coulombs divided by the number of seconds it took will give you the average amperage, which everything we're doing right now here is average. We're not thinking about instantaneous changes. We're considering all our current flow here to be constant. If we had 10 coulombs and to flow past the point in 1 second, we could have I equals 10 over 1 equals 10 amps, or 10 amperes. We have 5 coulombs in a second. We'll change these. Change this to a 5. This to a 5. 5 coulombs of charge travel past the point in the circuit in 1 second. We have 5 amps. So we see that a current is the movement of charges, and we measure it in a rate amperage, which is basically coulombs per second. If we have 0.3 coulombs, oh, we're not there yet. Okay, now we're going to talk about charge. The total charge that's moved is going to be equal to the intensity in amperage times the time in seconds. So if we have 1 coulomb if we have 1 amp of charge, 1 amp of current, and that current flows for 1 second, we will have 1 coulomb of charge moved. So charge, the quantity of charge that is transferred from one point to another, is the amperage times the time in seconds. Suppose that we have 0.3 amps. Our intensity is 0.3 amps. And our time was 0.2 seconds. So we would say that our charge would be equal to the intensity 0.3, and we'll multiply that times the time in seconds, 0.2 seconds. So we would have transferred from one point to another during that time 0.06 coulombs of total charge. So definitely charge and amperage are very, very closely related. They're not exactly the same thing. I'm going to give you a quick little math lesson here, a very small one. We had our formula for amperage intensity was equal to charge divided by time, and this charge per time makes it a rate of charge flow. If we wanted to solve for current, we would multiply both sides times T. I times T equals, and we multiply by T here, they would cancel, times T equals Q. So you can see the relationship there. Current was equal charge moved per time, and charge moved is the rate current, the rate of flow movement of charge, times the time during which it moved. So you can see these are very, very closely related. They're just solving Here, this one's solved for I, that one's solved for Q. They're basically the same equation solved for a different variable. In general, in wires, metals, we have free electrons that are moving, and those are our charge carriers, and we often call it an electron current or electron flow. And electron flow, electron current, or we could also call it electron flow, is from negative to positive. We have conventional current that we'll see talked about, and conventional current goes from positive to negative. In a wire, our current carriers are moving electrons, so we very often think of the electron currents going negative to positive. In solutions, as we pass current through a ionized solution, we have both negative and positive carriers, so we will see positive carriers going from the positive to negative terminal, and we'll see the negative ions, negative charge carriers going from negative to positive. So positive to negative conventional current flow, as I talked, is a real thing. It's just in electronics we usually think of electron flow and typically just call it current. We'll talk a little bit more about the different types of current. We've already talked quite a bit about electron current, which we may also call electron flow, and we showed that in the battery. We have ions, and that we talked a little bit about. And ions can appear in gases, and so a typical place you might see ions is in a liquid solution. Say we took pure distilled water and we add regular table salt, which we call sodium chloride. When we dissolve that sodium chloride in here, we're going to get some sodium ions, which are positively charged. We're going to get some chlorine ions, which are negatively charged. If we put an electrode into each thing here, into the solution, and we connect that to a battery, we'll draw a battery here, negative, positive. We will create, just like we did on the wire, we will have a negative Q here on this electrode, and we'll have a plus Q on this electrode, which will cause these negative chlorine ions will flow this way, and the positive sodium ions will be, the negative charge repels that negative ion, moves it towards the positive charge. The sodium, which is a positively charged ion, will be just the opposite. It will be attracted by the negative Q created by the battery on this terminal, and it will be repelled by the positive Q created by the battery on this other electrode. So we see that we really do have positive and negative charge carriers in this type of a situation. We're going to talk just a little bit about what we call hole flow. In semiconductors, say this was silicone, could be others, and if it's a P-type material, what that basically means is that we have, I'm going to draw the atoms as little boxes in this case just to make the illustration a little simpler to see. And in each of these little atoms we might have a missing electron, 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 missing electron. Now these missing electrons cause these atoms to be positively charged, plus charge. If we apply a battery to this piece of semiconducting material, again we end up with our negative Q charge here, our positive Q charge here, created by the potential difference of the battery. Now, what happens is an electron will jump from here to here and fill this hole because it's repelled by this negative charge. And then the electron will jump to here and fill this hole. So we get electrons moving like this, but as you can see, each time, once this electron jumps to here, this is no longer a positively charged atom. But when that electron jumps to here, this one's not positively charged, and the hole or missing electron appears again at this atom. So we have electrons moving from the negative to positive charge, but we have holes or missing electrons existing in each of these atoms which are moving in the other direction. When we fill a hole here, we fill a hole to the right, we created a hole to the left. This is a solid, this semiconducting material. So the nucleus of the atoms, which contains the protons, cannot actually move. So even though we have positive charges going this way as holes, we still have negative charges going this way as electrons, and they're creating holes as they move from one atom to the other. The protons, the actual positive charge carriers, do not actually move here because they're locked into the nucleus of the atoms in this solid semiconducting material. Now we're going to talk a little bit about the magnetic fields that occur around a current flow. We have a battery here. And we have a wire flow connecting this battery from one side to the other. And we're going to draw just a plane that wire is cutting here. Now we have here, this is negative, positive, so we have electron flow. And that's going in an upward direction through that plate. If we put a bunch of little iron filings on here, they would allow us to see the magnetic field that occurs around this wire. They would line up with that magnetic field around that wire. And the way that they would line up in semicircles around that wire with the electron, I'm just going to draw two of them. It's hard. It makes a mess if I draw too many more. Now, the arrows, the direction of this magnetic field is determined by what we call a right-hand rule. Now, The right-hand rule means that if we put our thumb in the direction of conventional current flow, which is actually opposite of electron flow, our fingers will curl in the positive direction of that magnetic field that will form around that wire. And there's always a magnetic field around moving charges. And if you've ever seen a electromagnet or something, this is why, because we pass current through the wire, we form an magnetic field around the wire as a result of the current flow, which we can intensify by winding a coil and adding all of these little magnetic fields together. But the important thing right here, right now, is that we do have a current flow creates a magnetic field around a wire, which will become more and more important as we get further along in this course. Talk a little bit about resistance. First, we're just going to show the symbol, the schematic symbol for a resistor. I'm just going to draw that over here. The schematic symbol for a resistor is basically just a zigzag line. It's a resistor. And R, the resistance, is measured in ohms, which we usually represent with the Greek letter omega. And resistance is an opposition to current flow. We had earlier a battery with the small amount of resistance in the wire, there'd be an awful lot of current here, probably more than the battery could supply. But by putting a resistor in here, we're basically able to control and reduce that current flow. R in ohms. I sometimes think of resistance as kind of like electrical friction. And like electrical friction, it will create heat when you pass current through that resistor. And let's talk just a little bit. Let's say we had 120 volts here. And suppose this resistance was 24 ohms. Now, with the voltage and the current, we can calculate, or voltage and resistance, we can calculate current. Basically, V over R equals I. So you'll often see this as E, but we're going to use V for voltage rather than E for electromotive force in this particular course. 120 volts divided by 24 ohms. That's going to be 5 amps. 120 divided by 24 will be 5. So you can also see by looking at this, if I increase the voltage, the current will go up. If I increase the resistance, the current will go down. Sometimes we use what's called conductance. And conductance is very simple. It's just 1 over the resistance. So if we had R equal to 10, 1 over 10 would be equal 0.1 or 1/10. So conductance would be 1/10, and the symbol for conductance is G. So we would have 1 over R equals G. And with our example here, that's 1 over 10 equals 0.1. And the current unit we use is called Siemens, and we indicate that with a big capital S. And this is in honor of Ernest von Siemens, who was involved in development of some of the electrical stuff. Now the conductance. Conductance G, and that's in Siemens. The older term was Mohs. So you might see that's, which is just ohm spelled backwards. And it's 1 over R equals G. So it's basically the electrical, the mathematical reciprocal of the resistance. Why would we use it, something as conductance? Some types of problems are easier to work out using conductance than they are with ohms. For now, just remember that conductance is the reciprocal of ohms, and it's the unit called Siemens, which I'll write that down here. Conductance is G, and it's in Siemens, Siemans. Now we're going to talk about a little bit more about complete circuits and such. Measurement of voltage, measurement of resistance, so on, measure of amperage. So I'm going to draw another circuit here with another resistor. Put 1.5 volts on here, and we put 300 ohms. Now this could represent, this 300 ohms could represent the filament resistance of a small light bulb. We would typically draw a light bulb something like this with a little coil and a circle around it. We're just going to represent the resistance of the light bulb here with just a symbol of the resistor. This would be a pretty small amount of current with this low voltage and relatively high resistance. It would be, we would end up, when we did the V over R, we'd have 1.5 over 300, and that would be I think that'd be 0.05 amps. Let's do the, we'll double check our work here. 300 times 0.005, 503, 0.15. Yeah, 1.5. We'll do it a little more carefully here. 0.15. I move this by 3 points. Yeah, we have 1.5 volts. So this closed or complete circuit allows current to flow through that resistance, which we're using to represent the resistance of a small light bulb, and the current is 5.05 amps, which we might also call 5 milliamps, because a milliamp is 1,000th of an amp. And you can see that this number here is 5,000ths of an amp, so we can call it 5 milliamps. We often do use in electronic circuits where the currents are not very large, we use symbols such as milliamps rather than amps, units such as milliamps. Now, we're going to think about measuring voltage and measuring current. If we wanted to measure the voltage across this resistor, we'll draw a little symbol for a meter here. I'm just going to call voltmeter. We would just connect it right across there. And we're going to see on this voltmeter, we're going to see the 1.5 amps or 1.5 volts of our power supply, battery. If we take the resistor out of there, we will still see the 1.5 volts potential difference provided by the battery. So as long as you don't overload the supply, so drawing some voltage or some current off of this supply will not change the voltage output of it. And that's what we call an ideal supply. If this was a little pin light cell and we tried to draw 100 amps off of it, it'd probably drop way down. It ain't capable of supplying that much current because it's not in reality an ideal supply. The voltmeter can be just applied anywhere in the circuit to read the voltage, but it's a little more difficult to measure amperage. We calculated earlier that we had 0.005 amps in this circuit, and that's basically the amount of charge moving past at a given point in a certain time. Now, how would we measure that? Well, to measure amperage, we have to break the circuit. I'm going to call this, I'm going to say amp meter, and we have to insert the leads of the amp meter into the circuit. So now the current is flowing, electrons are flowing from the battery through the amp meter, back through the resistor. So now the amp meter becomes part of the circuit. Amp meters are designed with very, very low resistance, so they don't change the circuit significantly when you put them in the circuit. But to measure amperage with a conventional ampermeter in the circuit, you have to break the circuit and make the ampermeter part of the circuit. Whereas you saw with the voltmeter, we just put it wherever we wanted to read the voltage. We didn't have to change the circuit any. But when we put a voltmeter on there and we measured the voltage here, we measured the voltage here, or we measured the voltage from here to here, the potential difference, we saw the same as the battery. Our current continued to flow. We break the circuit, remove the resistor, we no longer have current flowing. We have an open circuit. There is some very, very small amount of current flows to the voltmeter because the voltmeter is not an infinite resistance, but it's very high. So the effect of opening the circuit, the voltmeter's still there, still reading the voltage, but we're really drawing no more current. And by the same token, when we removed our amp meter, if we take it out of here, current no longer flows. So we need to have a complete path for charge carriers to get from one side of the voltage source all the way back to the other side of the voltage source in order to have actual current flow. Erase all this. So we saw how we opened our circuit and the current flow stopped. We removed the load, in the case of the load being the resistor, and saw that the voltage was still there, but no longer any current flow through the thing. We've talked about electron flow and conventional current flow. We're going to talk a little bit about DC and AC now. A battery will provide what is called DC. And what does DC mean? DC means if we have a load out here, we're going to put a resistor for a load. That at all times, with this positive potential difference, we have electron flow in this direction from negative to positive. We can vary that voltage if we have 1.5 volts, and we had 300 ohms, and we found by calculating voltage over resistance, we had 0.005 amps of current there. If we double the voltage, we change that to 3 volts, we now will have twice as much current, 0.010 amps. But it's still DC because the direction of the current flow was always the same. If we take this same we're just going to draw a resistor, not worry about what value. If we replace this battery with an AC source, now AC source, you notice we've drawn a little sine wave, and basically we have minus voltage, plus voltage. Initially, we start with 0 voltage, we move up in the positive direction, then we start to decline down, and then we go negative direction. So during this time, and we're going to measure this relative, I'm going to put a symbol for a chassis ground here. So we're measuring this voltage at this point, I'm going to call it point A, relative to this chassis ground. So while we're going positive, we have potential difference that looks like that. And during that time, when we're going positive, use the blue pen, we will have electron flow in this way. I'm going to write positive half cycle. And I'm even going to go a little further. I'm going to draw that part of it in blue to help you see what's going on here. So this blue positive half cycle will give at point A, which is what I'm measuring. I'm going to write point A here. The voltage at point A relative to my chassis ground. I'm going to call this chassis ground. I'm just going to call it ground. We always have to measure voltage relative to 2 points. We can't put one lead on and see anything. But during that time, we get current flow in this here counterclockwise direction. Now I'm going to draw the second half of this here voltage waveform in green. And during the green, we will have opposite polarity. We will have positive, negative when we measure at point A relative to ground. Now we will have current flow in the opposite direction. And I'm going to call this the negative half cycle. So you see in this positive half cycle, point A was positive with respect to our ground here, and that led to electrons flowing counterclockwise. During the negative half cycle, which I've drawn in green, we had point A being negative relative to ground, which led to electrons flowing clockwise around this loop. So with AC, we see that the direction of current changes. And in your typical house wiring, we usually have what we call, so we have a 60 hertz cycle rate. I'm going to draw a couple of waveforms here. 1, 2, okay, so one full cycle is one positive half cycle and one negative half cycle. Another cycle is another positive half cycle and another negative half cycle. So from here to here is one cycle, and when we have 60 hertz, we will have 60 of these cycles occur every second. Here's a second cycle. I'm going to say first cycle. I'm going to say second cycle. So we have here 2 full cycles. But you'll notice at this point, at the beginning of the first cycle, we had a change in direction, which I'm just gonna draw a little circle to dot that change in direction of the current flow. At this half cycle, we had another change in direction. At the end of the first cycle, beginning of the second cycle, we had another change in direction. And at this point, the change of we went from positive half cycle to the negative half cycle in the second cycle. We had another change in direction. We noticed for this cycle and this cycle, we basically 1, 2, 3, 4 change of directions, even though it was only 1, 2 cycles. So it's 120 hertz, means we have 120 full cycles every second. This is your household current. But we get, or 60 hertz, excuse me. So we have, when we run 60 hertz household current, 60 hertz, or 60 CPS, cycles per second, but we don't really use that too much anymore, so we'll cross it out. 1, 2, we get 60 full cycles per second, but we get 120 changes of direction, because we have to have one change for the positive half cycle, another change for the negative half cycle. So the number of changes of current direction is twice the frequency of the current flow, the AC current flow. Anyway, I think we'll end it there, and hopefully we'll see you next time, our next lecture I think we'll be talking a little bit more about resistance. And thanks for tuning in. Be sure to subscribe so you get notifications and such, and till next time, keep on learning.